Before we begin, please note that this presentation is for informational and educational purposes only. I am not a financial advisor, and the career information discussed here should not be considered a guarantee of income or employment. Your individual success will depend on your own effort, skills, and the market conditions at the time. Always conduct your own thorough research before making any significant career or financial decisions. Let me tell you about a guy named David. Maybe you know someone like him. Maybe you are him. David's 32, works in logistics for a mid-sized company in Ohio, and he's good at his job. He's reliable, he's smart, but he's hit a ceiling. A hard concrete ceiling. His annual raise, if he gets one, barely beats inflation. The idea of buying a house in his hometown feels more like a fantasy than a plan. He scrolls through Instagram and sees friends from high school who went into tech buying Teslas and vacationing in places he's only seen on a screensaver. And he feels this sinking feeling, this quiet panic that he missed the boat. That the world changed, the rules of the game were rewritten, and he was handed the old playbook. He hears words like AI, automation, and machine learning, and he doesn't feel excitement. He feels a knot in his stomach, wondering if a sophisticated spreadsheet is going to be doing his job in 5 years. What if I told you that David is standing at the edge of a gold rush? A digital gold rush so massive it's reshaping our entire economy, and it's happening right now, silently in the background of our lives. And what if I told you the pickaxe for this gold rush isn't a computer science degree from MIT, it isn't being a math prodigy, and it doesn't require you to already be living in Silicon Valley. It's a skill set that companies, from tiny startups to the United States government, are so desperate for. They are willing to pay six-figure starting salaries to people with no prior tech experience who can prove they have it. This isn't a fantasy. This is the reality of becoming a cloud engineer. And the central question we are going to answer today, with no fluff, no hype, just the hard facts, is this. Is becoming a cloud engineer the single best career move you can make in the United States for 2026 and beyond? I know what you're thinking. Here we go again. Another get-rich-quick in tech video. You're skeptical, and you should be. You've seen the ads for coding boot camps that promise the world and deliver a mountain of debt. You've heard that tech is full of layoffs and that you need to be some kind of genius to even get your foot in the door. And you're right to be cautious. But cloud engineering is different. It's not just another job in tech. It is the very foundation on which modern tech is built. And the demand for it isn't just a trend. It's a fundamental, irreversible shift in how the world does business. In this video, we are going to give you the complete blueprint. This isn't a high-level overview. We are going deep. We will break down what a cloud engineer actually does day to day. What does it feel like to do this job? We're going to pull back the curtain on the real salaries across the United States, not just in San Francisco, but in Texas, in Florida, in North Carolina, and for fully remote positions. We will show you the exact skills you need to learn, which programming languages matter, and which ones are a waste of your time. We'll talk about the big three: Amazon Web Services, Microsoft Azure, and Google Cloud, and help you decide which platform is the right one to bet your career on. And most importantly, we will lay out a step-by-step roadmap that can take someone from zero, from being David in logistics, to getting their first job offer as a cloud engineer. By the end of this presentation, you will have a clear, actionable answer and know if this path is right for you. So, why are we talking about 2026? Why the urgency? Because we are at a critical inflection point. To understand this, you need to understand what the cloud even is. For decades, if a company wanted to run a website or a software application, they had to buy a ton of expensive computer hardware, servers, and store them in a closet or a dedicated server room. They had to manage the power, the cooling, the security, the software updates. It was expensive, inefficient, and it didn't scale. Then, companies like Amazon, Microsoft, and Google had a revolutionary idea. They had already built these massive, world-class data centers for their own needs. What if they rented out slices of their computing power to other businesses? That's all the cloud is. It's not a magical, fluffy thing in the sky. It's someone else's computer. It's renting, not owning. This simple idea changed everything. It allowed a couple of kids in a dorm room to build an app like Instagram and scale it to millions of users overnight without ever buying a single server. It allows Netflix to stream petabytes of data to hundreds of millions of homes without a flicker. It allows your local hospital to securely store patient records and your bank to process your transactions instantly. The cloud is the invisible infrastructure that powers nearly every single digital interaction you have all day. And the people who design, build, and maintain that infrastructure, Those are the cloud engineers. They are the architects and civil engineers of the digital world. This transition from owning servers to renting them in the cloud is not a small trend. It's a mass migration. Every company, from Ford Motor Company to your local pizza place with an online ordering system, is moving to the cloud to save money, become more agile, and stay competitive. This migration alone has created a staggering number of jobs. But now, something else is happening. A new catalyst is pouring gasoline on this already raging fire. Artificial intelligence. You've seen the headlines about ChatGPT, about AI creating art, about AI discovering new drugs. What you don't see is the colossal infrastructure required to make that AI work. Training a large language model like GPT-4 requires more computing power than a small country. That power doesn't come from a laptop. Comes from the cloud. Thousands upon thousands of specialized servers, all networked together, all managed, secured, and optimized by, you guessed it, cloud engineers. The AI revolution is fundamentally a cloud revolution. AI isn't replacing cloud engineers. It's creating an unprecedented, explosive demand for them. For every new AI application that launches, an army of cloud engineers is needed behind the scenes to build and run the digital factory that makes it possible. This has created a massive talent gap in the United States. A chasm. A 2023 report from an industry analyst firm showed that over 90% of IT leaders see a significant shortage of cloud computing skills in the market. Companies have the money, they have the need, but they cannot find the people. Think about what that means for you. This isn't like applying for a marketing job where 150 people are fighting for one spot. This is a market where companies are fighting over qualified candidates. That means higher salaries. That means better benefits. That means more negotiating power. It means you are in the driver's seat. And this isn't a story confined to the coasts anymore. The pandemic shattered the myth that you had to be in a specific zip code to have a high-impact tech career. Companies are now hiring cloud engineers remotely from all over the country. They care less about where you are and more about what you can do. This opens up six-figure opportunities for people in Iowa, in Alabama, in Montana, places that were historically left out of the tech boom. It allows you to have a Silicon Valley salary while enjoying a lower cost of living, creating a level of financial freedom that was unimaginable just a decade ago. So for someone like David, stuck at his logistics job, this isn't just about switching careers. It's a chance to leapfrog into the very heart of the new economy. It's a path to financial security, to work that is constantly evolving and intellectually stimulating, and to a future that isn't threatened by automation, but is instead empowered by it. It's a ticket to a completely different life. But, and this is a very important but, this path is not easy. It's filled with potential pitfalls. You could waste thousands of dollars on the wrong certification. You could spend 6 months learning a technology that's already becoming obsolete. You could build a perfect resume that still gets ignored by every recruiter. There is a right way and a wrong way to do this. The internet is full of bad advice that can lead you down a dead-end path. So, how do you navigate this? How do you separate the signal from the noise and ensure you become one of the success stories? That's exactly what we're going to break down starting right now. Let's get into it. First, let's cut through the jargon and the buzzwords. What does a cloud engineer actually do all day? It's a question that gets a lot of fuzzy answers online, but the reality is both more complex and way more interesting than just managing the cloud. Think of a cloud engineer as the master architect, lead construction manager, and chief maintenance officer for a company's entire digital world. But instead of building with steel and concrete, they build with services from Amazon Web Services, Microsoft Azure, or Google Cloud Platform. Before the cloud, if a company wanted to launch a website or an app, they had to go through a painful, expensive, and slow process. They had to buy physical servers, big, loud, expensive boxes of metal and silicon. They had to rent space in a data center, a secure, air-conditioned warehouse to store them. They had to hire people to install them, network them, and pray they didn't break down in the middle of the night. If their website suddenly got popular, like after a Super Bowl ad, it would crash because the physical servers couldn't handle the traffic. They were stuck. The cloud changed everything. Companies like Amazon, Microsoft, and Google built unimaginably massive data centers all over the globe and said, hey, instead of buying all this expensive hardware yourself, just rent ours. Pay only for what you use, and you can scale up or down in seconds. This is where the cloud engineer comes in. They are the wizards who take that incredible raw power and shape it into something useful for a business. They don't just click a few buttons. They design the blueprint. They ask the critical questions. How do we build this system to be secure from hackers? How do we make it resilient so if one part fails, the whole thing doesn't collapse? How do we ensure it's lightning fast for a user in New York City, and just as fast for a user in Los Angeles? And crucially, how do we do all of this without spending a fortune? Let's walk through a hypothetical day. It's 8:30 a.m. on a Tuesday. You're a cloud engineer at a fast-growing e-commerce company. You grab your coffee and log into your dashboard. The first thing you do is check the health of the entire system. You're looking at dozens of metrics: server CPU usage, database response times, network traffic. Everything looks green. Good. At 9:15 a.m., you join a stand-up meeting with the software development team. They've just finished a new feature for the website, a personalized recommendation engine. Your job is to deploy their code, but you can't just drag and drop it onto a server. That's a recipe for disaster. Instead, you use a process called CI/CD, or continuous integration and continuous deployment. You've built an automated pipeline. You push a button and this pipeline automatically tests the new code, packages it up, and deploys it to a staging environment, a perfect clone of the live website, without any human intervention. You and the team test it there. It works perfectly. At 11 a.m., you get an alert, a high-priority one. The system is flagging an unusual pattern of traffic from a specific region, and database read times are slowly creeping up. This isn't a full-blown outage, but it's a warning sign. A fire starting in the distance. This is where your troubleshooting skills kick in. You dive into the logs and monitoring tools. It's like being a detective at a digital crime scene. You trace the requests, analyze the database queries, and after 45 minutes of intense focus, you find the culprit. A poorly optimized query linked to the new recommendation engine is putting too much strain on the main database under certain conditions. You work with the developers to quickly roll back that specific part of the feature and schedule a fix. You just prevented a major slowdown that could have cost the company thousands of dollars in lost sales. The afternoon is about building for the future. You spend a couple of hours writing infrastructure as code. Instead of manually setting up servers and databases by clicking through a web console, you write code that defines the entire infrastructure. This is a game changer. It means you can recreate your entire system in a new region of the world in minutes, not weeks. It's repeatable, less prone to human error, and it's one of the most in-demand skills a cloud engineer can have. You're essentially writing the DNA for your company's digital presence. Before you log off, you have a planning meeting with the finance team. They want to understand next quarter's cloud bill. You walk them through the spending, highlighting how you saved 15% last month by automatically shutting down development servers at night, and by switching to a more cost-effective type of data storage. You're not just a tech person, you're a business partner, directly impacting the bottom line. That's just one day, and it highlights the different hats you wear. But cloud engineer is also a broad umbrella term. Just like there are different types of doctors, there are different specializations in the cloud world, and understanding these is key to finding your fit. First, you have the cloud infrastructure engineer. These are the true builders. They are masters of the core components: virtual servers, storage, databases, and networking. They lay the digital foundation that everything else is built upon. If you love thinking about systems, how they connect, and how to make them robust and scalable, this is a great path. Then there's the cloud security engineer. In a world of constant cyber threats, these are the digital guardians. They design and implement security measures to protect the company's data and infrastructure from hackers. They set up firewalls, manage user access, scan for vulnerabilities, and respond to security incidents. If you have a passion for cybersecurity and a mindset of always thinking about what could go wrong, this specialization is incredibly valuable and in high demand. You also have the DevOps engineer or site reliability engineer, SRE. This is one of the hottest areas. These engineers live at the intersection of software development and IT operations. Their primary goal is to automate everything. They build the CI/CD pipelines we talked about, they create sophisticated monitoring and alerting systems, and they focus on making the entire process of building and running software faster, more efficient, and more reliable. If you love efficiency and finding clever ways to eliminate manual, repetitive work, DevOps is for you. Finally, there are even more niche roles like cloud network engineer, who focuses specifically on the complex networking in the cloud, or a cloud data engineer, who builds the pipelines to move and process massive amounts of data for analytics and machine learning. The key takeaway is this: a cloud engineer is a problem solver. They are the critical link between the abstract power of the cloud and the tangible goals of a business. They enable a small startup to compete with a global giant. They allow a company to serve millions of customers without ever buying a physical server. They are the architects of the modern digital economy. So we've established what a cloud engineer does, and why their role is so fundamentally important to almost every modern company in the United States. They are the ones turning the promise of the cloud into a reality, one line of code, one automated pipeline, one solved problem at a time. But this brings us to the multi-million-dollar question, or rather, the six-figure salary question. Given how critical this role is, what does the compensation actually look like? Is the demand really as high as the hype suggests? And what can we realistically expect it to be in 2026? We're going to dive deep into the numbers, the salaries, the job growth projections, and the regional differences across the US that you need to know about. The data might just surprise you. Alright, let's cut right to the chase. The money. Because let's be honest, while passion for technology is great, you also want a career that provides financial security and freedom. And when it comes to cloud engineering, the numbers don't just talk, they scream. According to data aggregated from sites like Glassdoor, Levels.fyi, and the US Bureau of Labor Statistics, the average base salary for a cloud engineer in the United States right now hovers somewhere between $125,000 and $145,000 a year. Let that sink in. The average. This isn't some mythical top-tier salary. This is the middle ground. But average is a loaded word. It doesn't tell the whole story. Your journey, your salary will depend heavily on your experience. So let's break it down into a realistic career trajectory. First, the entry-level or junior cloud engineer. This is you, maybe a year or two into your tech career, or perhaps you're making a switch from IT support or system administration. You've got a certification, maybe an AWS Certified Solutions Architect Associate, and you've built some projects. For this role, you can realistically expect to start in the range of $90,000 to $115,000. Now, some of you might hear that and think, only $90,000? But remember, at this stage, a company is taking a chance on you. You're being paid to learn and grow, to absorb knowledge from senior engineers while providing real value. It's a launchpad, and it's a very, very well-paid launchpad compared to almost any other industry starting point. Now let's fast forward 2 to 4 years. You're no longer the new person. You've been in the trenches. You've handled production outages. You've designed and deployed new infrastructure. You understand the trade-offs between cost, performance, and security. You are now a mid-level cloud engineer. This is where the first significant jump happens. Your salary range explodes to $130,000 to $170,000. You've proven your worth, you're a reliable and independent contributor, and your compensation reflects that directly. This is the stage where you start to feel real financial momentum, but the ride doesn't stop there. After 5, 7, or 10 years of dedicated work, you become a senior or a lead cloud engineer. You're not just executing tasks anymore. You're setting the strategy. You're mentoring junior engineers, making high-level architectural decisions, and solving the company's most complex problems. At this level, base salaries regularly push past $180,000 and can easily exceed $200,000. And this is where the conversation has to evolve beyond just salary. We need to talk about total compensation, or TC. This is the secret language of high earners in tech, and it's what separates a great living from generational wealth. Total compensation is your base salary, plus your annual bonus, plus, and this is the big one, your stock grants, often given as restricted stock units or RSUs. Think of RSUs as a promise from the company to give you shares of its stock over a period of time, typically 4 years. So, a senior cloud engineer at a major tech company like Google, Microsoft, or Amazon might have a base salary of, say, $180,000. That's already fantastic. But then they might get a 15% annual performance bonus, which is another $27,000. And on top of that, they might receive a stock grant of $400,000 that vests over 4 years. That's an extra $100,000 per year. So you add it all up. $180,000 base plus $27,000 bonus plus $100,000 in stock. Suddenly, their total compensation for the year is over $300,000. And for specialists in high-demand areas like cloud security or machine learning infrastructure, those TC numbers can soar to $400,000, $500,000, even $600,000 a year. This isn't a fantasy. Go to Levels.fyi right now and you will see these numbers verified by real employees. This is the financial reality at the top end of the cloud engineering world. Of course, a huge factor in all of this is location. A salary in rural Nebraska is not going to be the same as in downtown San Francisco. The traditional tech hubs, we're talking the San Francisco Bay Area, Seattle, and New York City, still command the highest salaries on paper. A senior engineer in San Jose might pull in a base of $220,000, while the same role in another city might be $180,000. But, and this is a massive but, you have to factor in the astronomical cost of living. That higher salary can get eaten up pretty quickly by a $7,000 a month apartment and $10 lattes. This is why the most exciting trend right now is the rise of emerging tech hubs across the United States. Cities like Austin, Texas, Raleigh, North Carolina, Denver, Colorado, and Atlanta, Georgia are booming. Tech companies are flocking there, and they're bringing high-paying jobs with them. While the salaries in these cities might be 10 to 15% lower than in the Bay Area, the cost of living can be 40 to 50% lower. This means your money goes so much further. A $160,000 salary in Austin can give you a quality of life that would require over $250,000 in Silicon Valley. You can own a home, have a shorter commute, and still be at the heart of a vibrant tech community. And the ultimate game changer? The normalization of remote work. The pandemic proved that high-level engineering work can be done from anywhere. This has decoupled salary from location for thousands of roles. It's now possible to earn a salary competitive with a major tech hub while living in a low-cost of living area. This is the holy grail for many, maximizing your earning potential while maximizing your quality of life. So the current financial picture is incredibly bright. But what about the future? What do these numbers look like as we head towards 2026? This is where we look at job growth. According to the U.S. Bureau of Labor Statistics, roles related to cloud computing, like information security analysts and network architects, are projected to grow at a rate described as much faster than average. We're talking growth rates of over 30% in the next decade for some of these roles. For context, the average growth rate for all occupations is around 5%. So cloud isn't just growing, it's exploding. Why? Because every single major industry is undergoing a digital transformation, and the cloud is the engine of that transformation. From healthcare moving patient records to the cloud, to the automotive industry developing self-driving cars that process petabytes of data in the cloud, to the entertainment industry streaming 4K movies from the cloud, the demand is insatiable. The rise of artificial intelligence and machine learning is adding rocket fuel to this fire, as these technologies require massive computational power that only the cloud can provide efficiently. This overwhelming demand and a relative shortage of highly skilled talent create the perfect economic storm for cloud engineers. It means salaries are not just stable. They are poised for significant continued growth. So what's a realistic salary projection for 2026? Factoring in continued high demand, competition for talent, and inflation, it is very conservative to expect a 4 to 6% average annual increase in base salaries. That means the current average of around $135,000 could easily become an average of $155,000 to $165,000 by 2026. For senior roles, base salaries consistently breaking the $220,000 mark will become the norm, and total compensation packages in the $350,000 to $500,000 range for top-tier individual contributors will be more common than ever. The evidence is overwhelming. The money is there, the growth is undeniable, and the future is incredibly secure. From a purely financial and job security perspective, becoming a cloud engineer is one of the smartest, most strategic career moves you can make in the United States today. But let's be real, you don't just wake up one day and walk into a $150,000 job. It's not a lottery ticket you can just buy. It's a prize you have to earn. So what does it actually take? What are the non-negotiable, must-have skills that separate the candidates who get the life-changing offers from the ones who get ghosted by recruiters? What's the real difference between someone who gets stuck at a junior level and someone who is on the fast track to becoming a highly paid cloud architect? That's the critical information we're breaking down next. The difference is deceptively simple, yet it's the single biggest reason why the cloud industry has two completely different career tracks. It's not about having more certifications. It's not about going to a fancier boot camp. It's not even about being a coding genius. The difference between the person who stalls out and the person who skyrockets is this: one learns to collect tools and the other learns to solve problems. Let me explain. Imagine two aspiring cloud engineers. Let's call them Certificate Charlie and Problem Solver Priya. Both are smart, both are motivated, and both are starting from roughly the same place. Charlie looks at the job descriptions and sees AWS Certified Solutions Architect everywhere. So he makes that his mission. He buys the top-rated course. He spends 3 months memorizing every single detail about EC2 instance types, the nuances of S3 storage tiers, and the specific API calls for DynamoDB. He lives and breathes flashcards. And he does it. He passes the exam with a great score. He proudly adds the badge to his LinkedIn profile and starts firing off applications. He's done what the industry told him to do. Priya takes a different approach. She sees the same job descriptions, but instead of focusing on the certification badge, she focuses on the responsibilities listed: design and deploy scalable, highly available and fault-tolerant systems, implement cost control strategies, automate infrastructure. She realizes the certification is just a proxy for being able to do that stuff. So her goal isn't to pass a test, it's to build something. She comes up with a simple project. A website where her family can upload photos and it automatically creates galleries. A seemingly trivial project, but it forces her to confront real-world problems. First, where do the photos live? She researches and learns about S3, but not just the textbook definition. She has to figure out how to create a bucket, how to set permissions so it's not public to the whole world, and how to use different storage classes to save money on older photos her family doesn't look at often. She's not memorizing facts. She's solving a cost and security problem. Next, how does she handle the uploads? She doesn't want to run a server 24/7 just waiting for someone to upload a photo. That's expensive. This leads her down the rabbit hole of serverless computing. She learns about AWS Lambda. She builds a function that triggers every time a new photo is uploaded to her S3 bucket. That function automatically resizes the photo into a thumbnail, saving it to another folder. She has just built a real event-driven architecture. She didn't do it because a practice exam told her to. She did it because it was the most efficient solution to her problem. Finally, she wants to be able to tear down and rebuild this entire system with one command. She doesn't want to click through the AWS console for 30 minutes every time she makes a change. This forces her to learn the basics of infrastructure as code using a tool like Terraform or AWS CloudFormation. She writes a script that defines her S3 buckets, her Lambda function, and all the permissions. Now she can deploy her entire application in minutes, and it's repeatable and version controlled, just like a professional. Now let's put them both in an interview. The hiring manager asks a classic question. We have a legacy application running on a single server that experiences huge traffic spikes during product launches, causing it to crash. Our budget is tight. How would you propose we migrate this to the cloud? Certificate Charlie goes first. He's confident. He's seen questions like this on his practice exams. He says, I would use an auto-scaling group with EC2 instances. I'd place them behind an application load balancer to distribute the traffic. I'd use CloudWatch alarms to trigger scaling policies, maybe a step scaling policy based on CPU utilization, to add more instances during the spike. For the database, I would migrate it to RDS for managed service and high availability. It's a technically correct answer. It's the textbook answer. It's also the answer 1,000 other candidates gave. Then it's Priya's turn. She leans in and says, That's a great question. My first thought wouldn't be about the tools but about the business problem. The key constraints you mentioned are unpredictable spikes and a tight budget. A traditional auto-scaling approach with EC2 is a solid, reliable option, but it can be slow to react to sudden spikes, and you're still paying for idle capacity on your baseline instances. Given the budget constraint, I'd want to explore a serverless approach first. Could we re-architect parts of the application to run on AWS Lambda? That way, we would pay literally nothing when there's no traffic, and it would scale almost instantaneously to handle the launch spike. We would pay only for the compute time we use down to the millisecond. Of course, this depends on the application's architecture and whether it can be broken down into functions. If a full re-architect isn't possible, we could look at a hybrid approach, maybe using containers on AWS Fargate, which abstracts away the underlying servers and provides a middle ground between the control of EC2 and the cost efficiency of Lambda. To make a final recommendation, I'd need to know more about the application's runtime and dependencies. Do you see the difference? It's night and day. Charlie recited a solution. Priya diagnosed a problem. Charlie listed tools. Priya discussed trade-offs, cost, performance, and architectural complexity. She demonstrated business acumen. She showed that she doesn't just know what the services are. She understands why and when to use them. Who are you going to hire? Who are you going to trust with your multi-million-dollar cloud budget? It's not even a competition. This is the fundamental secret. The people who get stuck are the certificate Charlies. They treat cloud engineering like an academic subject to be memorized. They get the entry-level job, but they can't advance because their knowledge is a mile wide and an inch deep. They can't connect the technology to the business value. Recruiters can spot this from a mile away, which is why their resumes get lost in the pile. The ones who succeed, the ones on the fast track to six-figure salaries and principal engineer roles, are the problem solver Prius. They are T-shaped. They have broad knowledge across the ecosystem, the horizontal bar of the T, but they develop deep, practical expertise in a few key areas by actually building things, the vertical bar of the T. Their knowledge isn't theoretical. It's battle-tested. They learned it by breaking things, fixing them, and solving real problems, even if those problems were just for a personal project. So, the path to a successful cloud career in 2026 and beyond isn't about collecting the most certifications. It's about becoming a problem solver. It's about building a portfolio of projects that prove you can do the work. It's about being able to walk into an interview and not just answer questions but ask intelligent questions back. This begs the most important question of all. If building is the key, what exactly should you be building with? What are the non-negotiable, must-know technologies that form the foundation of almost every modern cloud role? Forget the hype and the endless list of 200+ AWS services. What is the core tech stack that truly matters, the one that will get you hired and promoted? We're about to distill the entire cloud landscape down to the essential few. Let's start by building a house. Not a physical one, but the digital fortress that runs every modern application you use. Your bank, your streaming service, your social media, they all live in a house built in the cloud. And a cloud engineer? You're the architect, the general contractor, and the master electrician all rolled into one. Trying to learn cloud by just memorizing AWS service names is like trying to build a skyscraper by memorizing the names of different screws in the hardware store. It's useless. You need the blueprint. You need to understand the foundational pillars. Pillar number 1, the bedrock. This is Linux and networking. I cannot be more clear about this. If you skip this step, your career is built on sand. Period. Every other skill we discuss will crumble without it. Why Linux? Because the cloud runs on it. Over 90% of the public cloud workload runs on Linux. Trying to be a cloud engineer without knowing Linux is like trying to be a chef who doesn't know how to use a knife. You're not just a user clicking buttons in a pretty web console. You are commanding armies of servers. And the language you use to command them is the command line, the terminal. You need to be comfortable navigating file systems, managing permissions, and writing simple shell scripts in Bash. A senior engineer can tell in 30 seconds if you actually know your stuff by watching you work in a terminal. It's the single biggest giveaway. It's the difference between someone who uses computers and someone who commands them. And right alongside Linux is its twin brother, networking. This is the plumbing and the electrical wiring of our cloud house. You can build the most powerful, most expensive server in the world, but if you can't connect to it, it's just a very expensive, very loud space heater. You absolutely must understand the fundamentals. I'm talking about IP addresses, subnets, and CIDR notation. What's the difference between a public and a private IP? How does DNS work to turn a name like google.com into an address a computer understands? How do firewalls and security groups work to allow the good traffic in and keep the bad traffic out? How do load balancers distribute traffic across multiple servers so your application doesn't crash during the Super Bowl? These aren't abstract college textbook concepts. These are the daily tools of a cloud engineer. When you create a virtual private cloud, or a VPC in AWS, you are literally drawing a blueprint of your own private network on the internet. You are defining the roads, the gates, and the traffic rules. If you don't understand the fundamentals, you're not building a fortress. You're building a digital shack with the doors wide open. So, with our bedrock of Linux and networking poured and set, we move to pillar number 2, the framework. This is the cloud provider itself, the big 3, Amazon Web Services, Microsoft Azure, and Google Cloud Platform. This is where people get paralyzed. They see the hundreds of services and ask, which one do I learn? Do I have to learn all of them? The answer is simple and strategic. Pick one. Pick one and go deep. The market leader is AWS. And it's typically the safest bet for a first-timer because more jobs ask for it. But Azure is a monster in the enterprise space, and GCP is a powerhouse in data and Kubernetes. The secret is that the concepts are 95% transferable. They all have the same core building blocks, just with different names and slightly different paint jobs. So what are those core building blocks? First, you need compute. This is the engine of your house. In AWS, it's called EC2. In Azure, it's virtual machines. In GCP, it's compute engine. It's just a server in the cloud that you rent. You need to know how to launch one, how to connect to it, and how to configure it. Second, you need storage. This is the warehouse. In AWS, the king is S3. In Azure, it's blob storage. In GCP, it's cloud storage. This is where you store files, images, videos, backups, anything. It's infinitely scalable and incredibly cheap. Third, you need databases. This is the organized library of your house. You have relational databases like AWS RDS or Azure SQL for structured data. Think spreadsheets of user information. And you have NoSQL databases like DynamoDB for less structured data. You don't need to be a database administrator, but you need to know how to launch a managed database and connect your application to it. Finally, and most critically, you need Identity and Access Management or IAM. This is the security guard and the key master of your entire house. IAM controls who can do what, who can launch a server, who can read from the database, who can access the storage. I've seen junior engineers make catastrophic mistakes here, like accidentally making a private S3 bucket full of customer data public to the entire internet because they didn't understand a simple IAM policy. Mastering the core services of one cloud provider, compute, storage, databases, networking, and IAM, is non-negotiable. Now our house is built. It has a foundation and a frame, but building it was manual. We clicked around in the console. Took time. What if a tornado hits and wipes it all out? What if our boss says, "I love this. Build me 100 more exactly like it by tomorrow?" This is where the amateurs panic and the professionals shine. This brings us to pillar number 3, the automation engine, more commonly known as infrastructure as code, or IAC. IAC is the architectural blueprint for our house. Instead of clicking buttons, you write code that describes your infrastructure. You write a file that says, "I need 5 servers of this size, 1 database of this type, and a load balancer connecting them all." Then you run a command and the cloud provider builds it for you perfectly every single time. The undisputed king of IAC is Terraform. While AWS has its own tool called CloudFormation, Terraform has become the industry standard because it's cloud agnostic. You can use the same language and workflow to build your house in AWS, Azure, and GCP. Learning Terraform is a massive career accelerator. Changes the game. It allows you to version control your infrastructure just like you version control application code. You can see who changed what and when. You can roll back to previous versions. You can create identical environments for development, testing, and production with a single command. Let me paint a picture for you. A major outage occurs. The ClickOps engineer, the one who builds things by hand, is frantically scrambling, trying to remember the 200 manual steps they took 6 months ago. The engineer who knows Terraform calmly goes to their terminal, types Terraform apply, hits enter, and watches as the entire infrastructure rebuilds itself from scratch in minutes. Who do you think is getting the raise? Who do you think is sleeping well at night? This isn't a nice-to-have skill anymore. In 2026, it will be the absolute baseline expectation for any serious cloud role. Finally, we have our 4th and final pillar, the assembly line. Our house is built and we have the blueprint to rebuild it instantly. But how do we get things into the house? How do we deliver the actual software, the applications that our developers are writing, onto our servers? The old way was messy. A developer would throw a zip file over the wall and say, "Good luck." It was a nightmare of conflicting libraries and dependencies. The infamous phrase, "But it works on my machine," echoed through every IT department. That era is over. The first part of the modern assembly line is containers, and specifically Docker. Think of Docker as the standardized shipping container of the software world. It doesn't matter if you're shipping bananas or flat-screen TVs. They all go in the same standardized box. Docker does this for code. It bundles an application and all its dependencies, every library, every configuration file, into a single, lightweight, portable package called a container. That container will run exactly the same way on a developer's laptop, on a testing server, or in production in the cloud. It kills the works on my machine problem forever. But what happens when you have thousands or even millions of these containers? You need a system to manage them. You need a port authority, a global logistics network. That is Kubernetes. Kubernetes is the container orchestrator. It's the brain that decides which server each container should run on. It handles scaling, automatically adding more containers when traffic spikes. It handles self-healing, If a container crashes, Kubernetes automatically replaces it. It is, without a doubt, one of the most powerful and in-demand technologies in the cloud world. It is also a beast to learn. But you don't need to be a top-level expert to get a job. You need to understand the core concepts, what pods, services, and deployments are, and how they work together to run a resilient application at scale. This entire assembly line, from a developer committing code, to it being automatically built into a Docker container, and then deployed onto a Kubernetes cluster, is powered by a process called CI/CD, or continuous integration and continuous deployment. Tools like GitHub Actions or Jenkins automate this entire pipeline. This is the beating heart of modern software delivery. So there it is. The 4 pillars. The bedrock, Linux and networking. The framework, one major cloud provider's core services. The automation engine, infrastructure as code with Terraform. And the assembly line, containers with Docker and Kubernetes. This is the tech stack that matters. This is the roadmap. It's not a random list of buzzwords. It's a cohesive system where each piece builds upon the last. This is your path to not just getting a job, but building a real, defensible, high-value career in the cloud. So let's break that roadmap down, layer by layer. And the first layer, the absolute bedrock on which everything else is built, is the one most people, in their rush to get certified, try to skip. This is the mistake that costs them jobs, promotions, and ultimately their longevity in this field. I'm talking about the fundamentals, not the sexy stuff, not the stuff that gets all the hype on Twitter. I'm talking about the engine room of the entire digital world, Linux and networking. Let's start with Linux. And when I say Linux, I don't mean memorizing a few commands you copied from a Stack Overflow post. I don't mean you know how to ls to list files. I mean truly understanding the operating system that runs over 96% of the world's top 1 million web servers. The operating system that underpins every major cloud provider. Amazon Web Services, built on a custom version of Linux. Azure, the fastest growing segment of their virtual machines are Linux-based. Google Cloud practically breathes Linux. Trying to be a cloud engineer without deeply understanding Linux is like trying to be a Formula One mechanic when you've only ever learned how to drive a car with an automatic transmission. Sure, you can operate the vehicle. You can press the gas and turn the wheel. But the second something goes wrong under the hood, the second you hear a sound that isn't normal, you are completely and utterly lost. You are at the mercy of the dashboard warning lights. In the cloud world, the dashboard is the AWS or Azure console. And I promise you, the most critical company-breaking problems will never, ever show up as a neat little red icon on your dashboard. You need to understand the Linux file system hierarchy. Why is /var different from /etc? You need to master file permissions, not just so you can pass a certification question on Chmod 755, but so you can diagnose why an application can't write to its log file and is crashing in production at 3 a.m. You need to understand process management. What's actually running on your machine? How much memory and CPU is it consuming? How do you kill a rogue process that's bringing a multi-million-dollar e-commerce site to its knees? And most importantly, you need to become fluent in the language of the command line. You need to master the shell, specifically Bash. This isn't about being some elite hacker from the movies. It's about efficiency and power. The things you can do in seconds with a well-crafted one-line command, chaining together tools like grep, awk, sed, and zargs, would take you 20 minutes of frustrated clicking through a graphical interface. Shell scripting isn't even programming, really. It's about automating the conversation you have with the machine. It's the skill that lets you manage 100 servers as easily as you manage one. This is non-negotiable. Now, let's talk about the second pillar of this foundation, the single biggest differentiator I see between a junior engineer who gets stuck and a senior engineer who becomes an architect. Networking. If Linux is the engine, networking is the entire transportation grid. It's the roads, the bridges, the traffic lights, and the postal service of the digital world. And it is, without a doubt, the area where most aspiring cloud engineers have the biggest, most dangerous gaps in their knowledge. Why? Because the cloud makes it so easy to ignore. You can spin up a server with a public IP address in 30 seconds. Just works. Until it doesn't. And when it doesn't, the person who only knows how to click the Create VM button is useless. The person who understands the fundamentals is invaluable. You have to know how IP addressing and subnetting work. You need to understand CIDR notation not as a confusing string of numbers, but as a way of carving out your own private, secure piece of digital real estate in the cloud. Your virtual private cloud, or VPC, is your fortress. Subnets are the different districts within your city. If you don't understand how to plan the addresses, you'll end up with chaotic, insecure, and unmanageable infrastructure. It's the difference between a master-planned city and a sprawling, congested slum. You must understand DNS, the domain name system. I call it the most important and yet most disrespected system on the internet. It's the phone book for the entire web. When DNS breaks, the internet breaks. For you, this means understanding how to point a domain name to your load balancer, what the difference is between an A record and a name, and how to use cloud-native DNS services like Route 53 or Azure DNS to create highly available, resilient applications. An engineer who says, "I'm not sure some other team handles the DNS," is an engineer who will never be trusted with a critical system. And you have to understand the protocols that carry the data. TCP versus UDP. What's the three-way handshake? Why does it matter for your database connections? You need to understand HTTP and HTTPS. What are status codes beyond just 200 OK and 404 not found? When your load balancer is reporting 503 errors, what does that actually tell you about the health of your backend servers? Let me tell you a quick story about an engineer I know. We'll call him David. David was on a team responsible for a major new product launch. 2 days before launch, the application started experiencing bizarre, intermittent failures. It would work for 5 minutes, then hang for 2. The cloud provider's health dashboard was all green. The application logs showed nothing. The developers swore their code was perfect. The infrastructure team swore the servers were fine. Everyone was pointing fingers. The stress was unbelievable. While everyone else was panicking, David, who had spent his weekends mastering the fundamentals instead of just chasing the latest certification, did something different. He SSH'd into one of the Linux servers. He didn't look at the fancy dashboards. He used a command line tool called dump to look at the raw network traffic, the actual ones and zeros flowing in and out of the machine. And there it was. Hidden from every dashboard, he saw a flood of TCP reset packets coming from the database. The application servers were trying to reuse connections that the database, due to an obscure timeout setting, had already closed. The application wasn't crashing. It was just waiting silently for a response that would never come. It was an issue buried deep in the networking stack. It took him 30 minutes to find a problem that had stumped a team of 10 people for 48 hours. He recommended a simple kernel parameter change on the Linux servers to adjust the TCP keep alive settings. The problem vanished instantly. In that moment, David wasn't just another engineer. He was a hero. He saved the launch. His career trajectory changed that day. Why? Because he didn't just know how to operate the cloud. He understood how it worked. He understood the bedrock. This is why we start here. These skills, Linux and networking, are your defense against abstraction. They are your superpower when the fancy tools fail. And they are the absolute mandatory prerequisite for everything else we are about to discuss. You cannot containerize an application effectively if you don't understand the Linux processes and namespaces you are isolating. You cannot build a secure and scalable Kubernetes cluster if you don't understand the complex networking that allows its pods and services to communicate. This foundation isn't the old way of doing things. It is the timeless way. It's what separates the button pushers from the architects. It's the difference between a career that plateaus at $100,000 and one that sails past $250,000 and beyond. Now that we've poured the concrete and laid the rebar for this foundation, we can start building the first floor. We can start talking about the technology that truly defines the modern cloud landscape. So let's start with the three titans, the three continents of this new digital world: Amazon Web Services, Microsoft Azure, and Google Cloud Platform, AWS, Azure, and GCP. If you take away nothing else from this section, burn those three names into your brain. They are the bedrock of the modern internet. Virtually every major company you interact with, from Netflix and Disney Plus to your bank and your favorite airline, runs a significant portion of its operations on one, or sometimes all three, of these platforms. They are not just companies. They are the fundamental infrastructure of the 21st century economy. Let's start with the undisputed king, the 800-pound gorilla in the room: Amazon Web Services, or AWS. Launched back in 2006, AWS had a massive head start, and it shows. It holds the largest market share, and because of that, it's often the default choice for startups and the platform with the most job postings. If you're wondering where to begin your journey, AWS is almost always the right answer. It's the New York City of the cloud world, bustling, massive, and if you can make it there, you can make it anywhere. But what is AWS? It's a collection of over 200 different services, which sounds terrifying. but you only need to master a core handful to be incredibly effective. Let's break down the absolute essentials. First, you have compute. This is the engine of the cloud. The flagship service here is called EC2, which stands for Elastic Compute Cloud. The easiest way to think of an EC2 instance is as a virtual computer that you rent by the second in one of Amazon's massive data centers. You can spin one up in minutes, run your code on it, and then shut it down. It's the workhorse of AWS. Alongside it is a revolutionary concept called serverless, with the main service being AWS Lambda. If EC2 is like leasing a car, you have it 24/7 and you're responsible for it. Lambda is like taking an Uber. You just tell it where you want to go, what code you want to run, and it handles everything else, charging you only for the milliseconds your code is actually running. It's a game changer for efficiency and cost. Next, you need a place to put things. That's storage. The most famous service in all of cloud computing is probably Amazon S3, or Simple Storage Service. Think of S3 as an infinite digital filing cabinet. You can store anything in it: images, videos, backups, website files, and it's incredibly cheap and durable. It's designed to never, ever lose your data. For your EC2 instances, you have EBS or Elastic Block Store, which is simply the virtual hard drive that attaches to your virtual computer. Then you have networking. How do all these virtual computers talk to each other and the internet securely? That's the job of the VPC, or Virtual Private Cloud. This is your own logically isolated private section of the AWS cloud. It's like building a digital gated community for your applications with firewalls and security guards, what we call security groups and NACLs, controlling exactly who and what can get in or out. And finally, every application needs a brain to remember things. That's databases. AWS offers a huge variety, but the two you must know are RDS and DynamoDB. RDS, the relational database service, makes it painfully easy to run traditional databases like MySQL, PostgreSQL, or even Microsoft SQL Server. It handles all the tedious stuff like patching, backups, and failover, so you can focus on your application. Think of it as a perfectly organized library. DynamoDB, on the other hand, is a NoSQL database. It's built for insane speed and massive scale. It's less structured, like a giant, super-fast index card system, perfect for things like social media feeds, e-commerce shopping carts, or gaming leaderboards. Mastering just these core services, EC2, Lambda, S3 VPC, and RDS/DynamoDB, makes you a formidable AWS engineer. Now let's cross the ocean to the second continent, Microsoft Azure. If AWS is the scrappy innovator that built the market, Azure is the established empire that has leveraged its immense power to become a dominant force. Azure is the number 2 player, and its strength comes from its deep, unbreakable ties to the corporate world. For decades, businesses have run on Windows Server, Office, SQL Server, and Active Directory. For these companies, moving to Azure is a natural, comfortable evolution. It's the path of least resistance. The beautiful thing is, if you understand the concepts from AWS, you already understand Azure. They just use different names. AWS EC2 virtual computers are simply called virtual machines in Azure. AWS Lambda is Azure Functions. Amazon S3 is Azure Blob Storage. The VPC is called a VNet for virtual network. RDS has its equivalent in Azure SQL Database and other managed offerings. It's like learning Spanish and then realizing you can already understand a huge amount of Italian. The underlying principles are the same. Azure's unique advantage, its moat, is its seamless integration with the Microsoft ecosystem. The ability to extend a company's on-premises Active Directory directly into the cloud for identity management is a killer feature that AWS has struggled to match with the same level of native simplicity. If you see a job posting for a cloud engineer at a large, established Fortune 500 company, especially one that isn't a tech-first company, there's a very strong chance they are an Azure shop. Finally, we arrive at our third continent, the land of data, analytics, and cutting-edge engineering, Google Cloud Platform, or GCP. While it's third in market share, don't you dare underestimate it. GCP is the platform built by the company that had to solve planet-scale problems before anyone else even knew they existed. Google practically invented the technologies that now run the modern cloud. GCP's core services again mirror the others. Compute Engine is their EC2, Cloud Functions is their Lambda, and Cloud Storage is their S3. But where GCP truly flexes its muscles is in data, machine learning, and containerization. Their service BigQuery is legendary. It's a serverless data warehouse that can run complex queries over petabytes of data. That's thousands of terabytes, in a matter of seconds. Feels like magic. Their AI and machine learning platform, Vertex AI, provides access to the same powerful models and infrastructure that Google uses for search, YouTube, and Google Translate. For companies whose business is data, GCP is an incredibly compelling choice. And then there's Kubernetes. Kubernetes is the open-source operating system for the cloud, a system for managing containerized applications at massive scale. And it was invented, designed, and open-sourced by Google. Their managed offering, GKE or Google Kubernetes Engine, is widely considered the best, most mature Kubernetes service on the market. This gives them immense credibility and a powerful foothold in the world of modern application development. So you have the big three platforms, but a great cloud engineer doesn't just live on one continent. They know how to use the tools that work across all of them. This is the meta layer of skills that truly sets you apart. First is containerization, specifically with Docker. Think of Docker as the invention of the standardized shipping container, but for software. Before Docker, getting code to run reliably on a developer's laptop, then a testing server, then in production was a nightmare of mismatched libraries and configurations. Docker solved this by bundling an application and all its dependencies into a single neat package, a container that runs exactly the same way anywhere. This was revolutionary. But if you have thousands of these containers, how do you manage them? That's orchestration, and that is Kubernetes. As we just mentioned, Kubernetes is the conductor of your container orchestra. It decides which server each container runs on, it scales them up to handle traffic spikes, and it automatically heals the system by replacing any containers that crash. It is complex, without a doubt, but it has become the undisputed standard for running modern, resilient applications. Knowing Kubernetes is no longer a bonus. It's rapidly becoming a core requirement for senior cloud roles. Finally, there's the philosophy of infrastructure as code, or IAC. The old way of setting up servers was to have a system administrator manually click through a web console, setting up each piece one by one. This was slow, error-prone, and impossible to replicate perfectly. IAC changes the game completely. You write code using a tool like Terraform to define your entire infrastructure, your servers, your networks, your databases, your firewalls in a text file. You then run that code, and the tool automatically builds everything for you in the cloud perfectly every single time. You can version control it, peer review it, and deploy the exact same setup to a test environment, a staging environment, and a production environment with a single command. The dominant tool in this space is Terraform. While each cloud has its own native tool, like AWS CloudFormation, Terraform is platform agnostic. It's the universal translator. Learning Terraform means you can define infrastructure on AWS, Azure, GCP, and more, all with the same language and workflow. It is one of the single most valuable and highest leverage skills a cloud engineer can learn today. And this skill, the ability to define infrastructure as code, is the cornerstone of a much larger, more powerful philosophy that has completely reshaped the tech industry. I'm talking about DevOps. Now, DevOps is a term that gets thrown around a lot. Some people think it's a job title. Some think it's a specific tool. It's neither. DevOps is a culture. It's a fundamental shift in how we build and deliver software. It's about breaking down the walls between the people who write the code, the developers, and the people who run the code in production, the operations team. Historically, these two teams were like oil and water. Developers would write code, throw it over a wall to operations and say, "Here, run this." Operations would then struggle to get it working, and if anything broke, the finger pointing would begin. It was slow, it was inefficient, and it was frustrating for everyone. DevOps changes that. It says, let's make these two teams one team. Let's give them shared tools, shared processes, and most importantly, shared responsibility. The goal? To deliver better software faster. And the engine that powers this DevOps culture is something called CI/CD. CI/CD stands for Continuous Integration and Continuous Deployment. Don't let the jargon intimidate you. Let's break it down. Continuous integration is the practice of developers frequently merging their code changes into a central repository. Every time they merge, an automated build and test sequence runs. This is huge. It means you catch bugs early right away instead of weeks later when you're trying to merge a dozen different features and everything is on fire. Continuous deployment is the next step. If all the automated tests pass, the code changes are automatically deployed to production. Yes, automatically. A developer can commit a line of code and minutes later, it can be live in the hands of users without any manual intervention. Think of it like a fully automated factory assembly line for software. Raw materials, the code, go in one end and a finished tested working product comes out the other, ready for customers. As a cloud engineer, you are the architect and the chief mechanic of this assembly line. You are the one who builds and maintains these CI/CD pipelines. And to do that, you need to know the tools of the trade. For years, the undisputed king was a tool called Jenkins. Jenkins is the old, reliable, infinitely customizable workhorse of the CI/CD world. It has a massive ecosystem of plugins that allow it to do virtually anything. If you've worked in tech for any length of time, you've almost certainly encountered a Jenkins server. And because it's been around for so long, thousands of companies still rely on it, making it a valuable skill to have. But in recent years, two new contenders have risen to challenge the throne, and they've done so by integrating the CI/CD pipeline directly into the place where code already lives. I'm talking about GitLab CI/CD and GitHub Actions. GitLab took a brilliant approach. They said, why should your code live in one place and your pipeline live somewhere else? They built a fantastic CI/CD system right into their GitLab platform. You define your entire pipeline in a single simple file called .gitlabci.yml that lives right alongside your code. It's clean, it's powerful, and it's all in one place. Then came GitHub Actions. GitHub, being the world's largest home for source code, saw what GitLab was doing and launched their own integrated CI/CD solution. And it has taken the world by storm. GitHub Actions is incredibly powerful because it's event-driven. You can trigger a workflow on virtually any event in your repository. A code push, a new issue being created, a comment from a team member. The flexibility is staggering, and the community has built a massive marketplace of pre-built actions you can drop right into your pipeline. For a cloud engineer in 2026, proficiency in GitHub Actions is non-negotiable. It is rapidly becoming the new standard. So you've used Terraform to define your cloud infrastructure. You've used GitHub Actions to create a pipeline that automatically tests your code. But what about the code itself? How do we package it up so it can run reliably anywhere? This brings us to the next revolutionary technology you must master: containers, and specifically Docker. Before containers, you had the classic developer problem. Well, it works on my machine. A developer would build an application on their laptop, which had a specific version of Python, a specific set of libraries, and a specific operating system. Then they'd hand it over to the operations team to run on a production server, which had a different version of everything. And of course it would break. The resulting chaos was a massive drain on time and resources. Docker solved this problem with a simple, brilliant analogy: the shipping container. Before standardized shipping containers, loading a ship was a nightmare of different sized boxes, barrels, and sacks. It was slow and inefficient. The shipping container standardized everything. It didn't matter what was inside: electronics, bananas, cars. It all went into the same standard box, which could be easily moved by any crane, truck, or ship in the world. Docker does the exact same thing for software. A Docker container packages up an application's code along with all of its dependencies, the libraries, the runtime, the system tools, everything it needs to run, into a single standard box. This container can then run on a developer's laptop, a testing server, or a massive production cluster in the cloud, and it will behave exactly the same way everywhere. The "it works on my machine" problem? Gone. Forever. As a cloud engineer, you'll live and breathe Docker. You'll write Docker files, which are like the blueprints or recipes for building your container images. You'll build those images and store them in a container registry, and you'll run those containers to power your applications. But this leads to a new problem. A single application might be composed of dozens or even hundreds of these containers, all needing to talk to each other. What happens if one of them crashes? How do you scale them up to handle a sudden spike in traffic? How do you roll out an update without taking the whole system down? Doing this manually for thousands of containers is impossible. You need an orchestrator. You need an air traffic controller for your containers. And in the world of container orchestration, there is one name that rules them all: Kubernetes. Kubernetes, often abbreviated Kubernetes, is an open-source project originally designed by Google, based on their internal system for running billions of containers a week. They open-sourced it, and it has since become one of the fastest-growing and most important open-source projects in history. It is the de facto operating system for the cloud. Kubernetes is the master conductor of your containerized applications. You simply tell Kubernetes what you want your desired state to be. You say, I want 3 copies of my web server container running at all times, and I want them to be accessible to the public internet. Kubernetes then takes over. It finds servers to run your containers on. It monitors their health. If one of the containers crashes, Kubernetes automatically restarts it. If a whole server goes down, Kubernetes automatically moves its containers to a healthy server. If you suddenly get a flood of traffic, you can tell Kubernetes to scale up to 30 copies of your web server, and it will handle it. When the traffic dies down, it will scale back down to save you money. It provides self-healing, automated scaling, and zero downtime deployments. It is the engine that powers the resilient, always-on applications we rely on every day, from streaming services to online banking. For a cloud engineer looking towards 2026, learning Kubernetes is not just a good idea. It is an absolute necessity. It is the pinnacle of modern infrastructure management. So let's put it all together. You use Terraform to codify the creation of a Kubernetes cluster. You use Docker to package your application into containers. And you use a CI/CD pipeline with GitHub Actions to automatically build those containers and deploy them onto your Kubernetes cluster. This entire workflow, IAC, CI/CD, containers, and orchestration, is the beating heart of modern cloud engineering. It's what enables companies to innovate at a blistering pace. And it's why cloud engineers who have mastered this stack are in such ridiculously high demand. But this stack, as powerful as it is, also introduces new complexities and new challenges. How do you secure this entire pipeline from start to finish? With so much automation and so many moving parts, a single vulnerability could be catastrophic. This is the central question that keeps CISOs, Chief Information Security Officers, up at night. And their answer has created one of the most lucrative and future-proof specializations in all of technology: cloud security. More specifically, the discipline known as DevSecOps. If DevOps was about merging development and operations to build and ship software faster, DevSecOps is about injecting security into the very heart of that process. It's a fundamental philosophy shift. For decades, security was treated as the final checkpoint. The developers would build the car, the operations team would get it ready for the road, and then, right before shipping, the security team would show up to inspect it. They'd point out the lack of seatbelts, the faulty brakes, the non-existent airbags. And the whole process would grind to a halt, sending everyone scrambling back to the drawing board. It was slow, expensive, and created a culture of animosity. Security was the department of no. DevSecOps flips that entire model on its head. It's a concept called shifting left. Imagine the software development lifecycle as a timeline from left to right. Left is the very beginning, the idea, the first line of code. Right is the very end, the application running in production. Shifting left means moving security from the far right of the timeline to the absolute earliest possible point. It's not about inspecting the car after it's built. It's about embedding security engineers with the designers and mechanics, ensuring the blueprints themselves include reinforced steel, crumple zones, and a fire suppression system. Security isn't a gate you have to pass through. It's a foundational material you build with from day one. So what does this actually look like in practice? How do you build security into an automated pipeline? It's a fascinating ecosystem of specialized tools that act as automated guardians at every single stage. When a developer writes a piece of code, even before they commit it, tools known as static application security testers, or SAST tools, are already at work. Think of them as an incredibly advanced spell checker, but for security vulnerabilities. They scan the raw source code, looking for common weaknesses like the ones that lead to SQL injection attacks, or even more simply, for secrets that have been accidentally hard-coded. Things like API keys, passwords, or database credentials just sitting there in plain text. A SaaS tool flags this immediately, right inside the developer's coding environment, preventing a catastrophic mistake before it even enters the system. Okay, the code is clean. The developer commits it, and our CI/CD pipeline kicks off the build process. Here, another guardian steps in: software composition analysis, or SCA. Modern applications are almost never built from scratch. They're assembled like complex Lego models using hundreds, sometimes thousands, of open-source libraries and packages. Each of those packages is a potential entry point for an attacker. An SCA tool acts like a meticulous supply chain manager. It scans a manifest of every single third-party component being used and cross-references it against a massive database of known vulnerabilities. This isn't theoretical. In late 2021, the world was rocked by the Log4j vulnerability. A single ubiquitous open-source logging library used in millions of applications had a critical flaw, effectively giving attackers a skeleton key to vast swathes of the internet. Companies who had robust SCA scanning in place were able to immediately identify every single one of their applications that used the vulnerable library and patch them. Those who didn't were left flying blind, scrambling for weeks in a panic. That's the power of SCA. Next, the application is built and deployed to a testing environment. This is where Dynamic Application Security Testing, or DAST, comes into play. Unlike SAST, which reads the source code, DAST interacts with the running application just like a real user or a real hacker would. It actively probes the application from the outside, bombarding it with malformed requests, trying to trick it into revealing secrets, looking for weaknesses in how it handles data and sessions. It's essentially an automated ethical hacker, testing the application's real-world defenses before it ever faces a real-world attacker. But we're not done. We're deploying this application inside a container, using our infrastructure as code. Each of these layers needs its own security. Before that container image is stored in a registry, it gets scanned. Tools like Trivy or Claire inspect every layer of the container, looking for vulnerabilities in the base operating system or any software packages installed within it. And that Terraform or CloudFormation code we wrote to define our infrastructure, that gets scanned too. Tools like Checkov or TSEC analyze the code before it's ever applied to our cloud account. They're looking for common misconfigurations that lead to breaches. Is that S3 bucket about to be made public? Is that firewall rule way too permissive, leaving a critical database exposed to the entire internet? This simple scan prevents insecure infrastructure from ever being created in the first place. Finally, the application is live, running in production on our Kubernetes cluster. The job still isn't over. This is where runtime security takes over. Tools like Falco act as a security nervous system for our live environment. They monitor everything happening in real time. Is a process inside a container suddenly trying to write to a system directory it shouldn't? Is an application making an outbound network connection to a suspicious IP address? Falco detects this anomalous behavior and can trigger an immediate alert or even automatically kill the suspicious process, containing a potential breach in milliseconds. This entire automated security pipeline, from the first line of code to the running application, is the world of the cloud security engineer. It's a role that requires you to be a master of all trades. You need to understand code like a developer, infrastructure like an operations engineer, and threats like a hacker. It's part detective, part architect, part firefighter. And because of this unique blend of skills, it is one of the most in-demand and highest-paid jobs in the entire technology sector. Why? Because the cost of failure is astronomical. A single major data breach can cost a company hundreds of millions of dollars in fines, recovery costs, and lost business. The Equifax breach was estimated to have cost the company over $1.4 billion. The reputational damage can be even worse, destroying decades of customer trust overnight. When a company weighs the cost of a multi-billion-dollar breach against the salary of a cloud security engineer who can prevent it, that salary starts to look like the best bargain in the world. This is why you see senior cloud security roles in the US regularly commanding salaries upwards of $180,000. $220,000, and even higher. There is a massive global talent shortage for people who can do this work. They are the guardians of the modern digital enterprise, and companies are willing to pay an enormous premium for that peace of mind. So, when we ask if becoming a cloud engineer is a good career path for 2026, looking at the security specialization, the answer is an unequivocal, resounding yes. It's a path that places you at the epicenter of a business's greatest risk and its greatest need. It's a field that is, by its very nature, constantly evolving, ensuring you'll never stop learning. As we push further into AI, serverless, and even more complex distributed systems, the need for integrated, automated security will only become more critical. This isn't just a job. It's a mission-critical function that is fundamentally reshaping how we build and trust technology. We've covered the core roles, the money you can make, the powerful DevOps toolchain, and the critical security layer that protects it all. We've essentially designed and built a high-performance, armored vehicle. But a vehicle, no matter how powerful, is useless without a skilled driver. We've talked about the what, but we haven't fully covered the who. What are the human skills, the non-technical traits, that separate a good engineer from a truly indispensable one? And most importantly, what is the exact step-by-step blueprint you should follow to go from where you are today to landing your first job in this incredible field? Alright, let's build that blueprint. Forget the vague advice you've seen on forums. This is the battle-tested, no-fluff roadmap from zero to hired. Think of it not as a checklist but as a series of 4 distinct phases you must conquer. Each one builds on the last, forging you into the kind of candidate companies are desperate to find. Phase 1. The unshakable foundation. You cannot, I repeat, cannot build a career in the cloud without a rock-solid understanding of core IT principles. Trying to learn cloud without this is like trying to become a novelist without knowing the alphabet. It's a recipe for disaster. So, what's in this foundation? First, networking. This is the circulatory system of the internet and of the cloud. You need to intimately understand how data moves from point A to point B. I'm talking about the TCP/IP model, the difference between TCP and UDP, what DNS is and why it's the phone book of the internet, how HTTP and HTTPS work to deliver the websites you browse every single day. When an application in the cloud isn't working 90% of the time, it's a networking problem. If you can't diagnose it, you can't fix it. You're not an engineer, you're just a liability. Second, operating systems. Specifically, you need to learn Linux. Yes, Windows servers exist in the cloud, but the vast, overwhelming majority of cloud infrastructure runs on Linux. You need to be comfortable in the command line. You need to understand file permissions, package management, and basic shell scripting. The command line is your scalpel. A graphical interface is a plastic toy knife. Real engineers use the scalpel. Get comfortable with it, make it your home because you will be living there. Third, a basic grasp of programming concepts. You don't need to be a code wizard yet, but you need to understand what a variable is, what a loop does, what a function is. This is about understanding the logic that powers the applications you'll be supporting. It's about speaking the same language as the developers you'll be working with. This first phase is the most overlooked, and it's the reason so many people fail. They jump straight to the fancy cloud services without knowing how the underlying technology works. Don't be that person. Build your foundation on granite, not sand. Phase 2, choose your kingdom. Once you have the fundamentals, it's time to pick your cloud platform. We have the 3 titans: Amazon Web Services, Microsoft Azure, and Google Cloud Platform. AWS is the undisputed market leader, the 800-pound gorilla. They have the widest array of services and the largest community. Azure is the enterprise darling, deeply integrated with Microsoft products that big corporations have used for decades. If you want to work for a Fortune 500 company, Azure is a powerful choice. And GCP is the innovator, a favorite among startups and tech-forward companies, renowned for its prowess in data analytics, machine learning, and containerization with Kubernetes. So which one do you pick? Here's the secret. For your first job, it matters less which one you pick, and more that you pick one and go deep. The core concepts, virtual machines, object storage, managed databases, virtual networking, they're the same across all 3. Learning one makes learning the others exponentially easier later on. My advice? Go to LinkedIn or Indeed, search for cloud engineer jobs in the city you want to live in, and see what companies are asking for. Let the market guide your decision. Pick the platform that has the most opportunity in your area and plant your flag. Phase 3. Claim your first trophy. This is where the theory gets real. You are going to get certified. Now listen closely. A certification is not a golden ticket to a job, but it is an invaluable, structured learning path and a critical signal to recruiters that you are serious. For your first one, you're aiming for the associate level certification on your chosen platform. For AWS, that's the AWS Certified Solutions Architect Associate. For Azure, it's the AZ-104, Microsoft Azure Administrator. For GCP, it's the Associate Cloud Engineer. Getting this certificate is your mission. It will force you to learn the breadth of the platform's core services. But how you study is what separates success from failure. First, invest in a high-quality video course from a reputable instructor. They've already organized the fire hose of information for you. Second, read the official documentation and white papers for the services you're learning about. This is what professionals do. Third, and this is the most important step of all, you must get your hands dirty. Theory will get you the certificate. Practice will get you the job. All cloud providers have a free tier. Use it every single day. Don't just watch a video about setting up a virtual server. Do it yourself. Break it. Fix it. Understand why it broke. Deploy a simple website. Set up a database. Build the muscle memory. The goal isn't just to pass a multiple choice test. It's to gain real practical skills. Which brings us to phase 4. Learn the language of automation. In the cloud, we don't do things manually. We automate. We write scripts and code to build, manage, and deploy our infrastructure. To do this, you need to learn a programming language. And for infrastructure and cloud engineering, the undisputed king is Python. You don't need to become a full-stack software developer, but you need to achieve proficiency. You need to be able to write scripts that interact with your cloud provider's API, for example, using the Boto 3 library for AWS. You should be able to write a script that automatically spins up a new server, or one that searches for and deletes old, unused storage buckets to save the company money. This is what a cloud engineer does. Python is your power tool. It's what allows you to manage an army of 10,000 servers with the same effort it takes to manage one. Alongside Python, you need to continue honing your shell scripting skills in Bash. Many daily tasks and quick fixes are best handled with a simple Bash script. So let's recap the blueprint. Phase 1. Build an unshakable foundation in networking and Linux. Phase 2. Choose your cloud platform based on market demand. Phase 3. Earn your first associate-level certification through intense, hands-on practice. Phase 4. Learn Python and the art of automation. This 4-phase plan is your path. It will take time, it will take grit, and it will challenge you. But if you follow it, you won't just be someone who wants to be a cloud engineer. You will have the fundamental, practical skills of one. But having the skills isn't enough. How do you prove it to an employer? How do you build a resume and a portfolio that makes you the obvious choice, even if you have no prior professional tech experience? That's where the real magic happens. That's how you bridge the gap from learner to earner.